Hey guys, welcome back. Well, I've been doing some imaging with the SCT, and I don't know about you, but when I think about the SCT and doing all the work that I have to do to use that scope, this is the mental image that always comes to mind. It's just a lot of stuff held together with a single thread. And in this case, the threads are collimation, which we talked about last week, finding guide stars in an off-axis guider, plate solving with a dark filter like a dual or tri-band filter that I'm using with my one-shot color camera, the ASI 294MC, and there's also our Nemesis camera fan vibration. All of these things can come in and really ruin your images, if not your entire imaging session. So I thought I'd talk about that a little bit today and some of the things that I'm doing to try to reduce some of these things. So everything's hanging by a thread. I had some imaging time during a full moon, and I knew I wasn't going to get much good imaging. The trouble is, I got even less than I expected, and I didn't expect much. One of the main things I was having are some plate solving failures using a tri-band filter with my long focal length scope, which means there's only a handful of stars available, and you've got to expose for a fairly long time to get those stars to come out. Focusing was working, but plate solving was just air. It was not working well. So what I thought I'd do is take out the filter drawer and put in a filter wheel so I have access to other filters that I can use for plate solving. Then if you do that, you got to change the back focus. And then when you do that, you got to refocus the off-axis guider for little changes that you've made to the back focus. So we'll talk a little bit about that and one of the techniques I use to try to get pretty decent focus through the off-axis guider. Now, there are very few guide stars, so I've always wondered if I could just get away with using a 200 millimeter guide scope, not much weight, just pull it off of my GT81 or my Red Cat 51, slap it onto the SCT and see if that works. So I did a little test while I had all this full moon time available. All in all, I'm going to win some and you're going to learn some when you do some of these experiments in a full moon. So buckle up and let's get started. The ZWO 5-position filter wheel. I don't need all the filters for a monochrome setup you would have to have with 7 filters. Instead, I just have 5 filters that I use with my one-shot color camera. I could get away with just using one filter in the filter drawer. It's just that I'm having these issues with plate solving and possibly focus. That was the main reason for going to the 5-position filter wheel, and I thought I could bring in the ZWO UV IR filter to help me do the plate solving and possibly do the focusing and just let all the other filters just be the imaging filters that I use. Here's what the filter wheel looks like with the filters placed in it. I've got the ZWO UV IR filter, the Optolong L Pro. It's a bit more light, but doesn't do a great job with galaxies and capturing the HA by itself. They have the Antlia Tri-Band filter, which does do a pretty good job of bringing in the red tones of the HA in those galaxies. And I've also got some nebula filters that I've been using only for nebula, the O3 and HA dual band filter and the H beta and S2 dual band filter. Now, with a filter wheel, it gives me an opportunity to bring and pair some of these filters together that I wouldn't ordinarily have done with just a filter drawer. For example, I could shoot with the Optolong L Pro light pollution filter and pair it with an H alpha filter in the filter wheel to get those HA beta in those galaxies. So that does bring in some flexibility. Plus, I can do all of the plate solving and possibly even focusing with the ZWO UV IR filter and not have to use the long exposure times that I would have to use with these darker filters in a filter drawer. So all in all, it seems like it's going to be an improvement that's going to help out, although it does add some weight to the scope. Anyway, if it just saves me from those plate solve failures I was having, that's a good thing. Now, if I do want to go ahead and use that UV IR filter for focusing as well as plate solving, one of the things that I need to check out is what is the difference between the various filters relative to the UV IR filter in terms of focus step size. So if I'm going to use focus offsets, do I have to use focus offsets? That's what I wanted to check out. I used the Bahtinov mask here and that software I mentioned in the last video, the SkyCal focus and collimation tool. And several tests with the same filter here, the UVR filter, move the focuser around a bit, got different Bahtinov pixel errors as reported up here in this upper line here or down in this number, this your word up here by the blue arrow. But I got these numbers coming out of the focus tool, the focus and collimation tool, and then I did some change to the L Pro filter. Also got the focus error here in the tri-band. Did a couple of tests with it. It was going to be some weird results, and did the two dual band filters here, but also moved the focuser some in here. But these first set of images here gave me a chance to find out what the correlation is between focuser position and Bahtinov focus error here. And this is what I came up with. A nice straight line, which is what you'd hope it would be. And it turns out it's about 1.83 steps of focuser movement gets you a +1 increase in the error, the focus error as reported by the SkyCal focus and collimation tool software. Now, I know there's no such thing as a 0.83 step, but just imagine here, if we go to the L Pro, you can see that we need to take this and move it to 0 from -1. So that's a +0.1 step. That means I need to go from 18,528 to 18,530, 2 steps, to get up here. So that's a two-step offset if you want to call it that. But if you go through all these combinations here and taking into account that I have moved the focuser here and this down here with these filters, this is the offsets that I come up with. I've got the 0 is my reference, so that's the UV IR filter. There's the 2 from the L Pro, 2 steps, positive focuser steps. So you would focus here and then you would just advance it by 2 steps for the L Pro, for example. Tri-band, I got some weird results. I'm going to throw out that upper one and maybe one day go back and reevaluate this middle one here just to see if the numbers are consistent. But -3 steps for the tri-band filter, and then oddly for the O3 and HA and the H beta and S2, it's basically just plus or minus 1 step. And when you consider that the focus zone, the critical focus zone for this setup is 16 focuser steps, these numbers here are down in the noise. So for all intents and purposes, I'm going to ignore all this. And when I focus with the UV-IR filter, I'm just going to use that focuser position to do the imaging with whatever other filter I've selected. If I'm going to put a filter wheel into the mix here, I've got to change the back focus yet again. This seems to be something I do on a daily basis. I got to cut that down. My previous setup had this set of arrangements. We won't go through that in detail. This is the new set of arrangements. I was trying to get to a 139 millimeter back focus. I had 138 before. I've got 140.7 now. That's less than 1% off of the total back focus, so I don't think it's a significant amount. But essentially what I've done is to put in the filter wheel, that's 20 millimeters thick, and that replaces a 21 millimeter thick filter drawer. I also took out the 11 millimeter spacer that was between the camera and the filter drawer, so now I'm up to a total of 12 millimeters of difference, but I have to use a spacer to go from the M54 thread of the filter wheel down to an M48 thread for this spacer here. You can just see that lip there. That's that spacer. That adds on to the 10 millimeter spacer. So that gives me a total of 12 millimeters here for this distance between the face, the back face of this filter wheel and the forward face of the spacer here. So that's why that's a 12. It's actually a 10 plus a 2. And then I get into the off-axis guider adapter and the off-axis guider body. Altogether, this net change meant that I moved the camera in by 10 millimeters. And of course, when you have an off-axis guider, when you make that kind of a change, you got to move the off-axis guider down by 10 millimeters. And it actually was very convenient. I've got this parfocal ring on here and the camera is held in place with these 2 set screws with the off-axis guider. So it's held in place, just loosen that up, and then using a micrometer, raise that part focal ring up by 10 millimeters, tighten the screws back in to lock it onto the camera body, and then just drop the camera down and reset the thumb screws, and that should be still in focus, but of course, it's something you want to check out. So I was pretty confident that I was still going to be able to see the guide star because I was in focus before and pretty darn close here, but I want to check that out. Another thing that you don't want to be doing too much is changing the focus of your off-axis guider. So it's very important when you have the 2 configurations with this setup, my native focal length at 2315 millimeters focal length, and the configuration with the focal reducer, which takes the focal length down to about 1400 millimeters. The thing you want to make sure of is to try to keep all of the spacers and optical links that are between the camera sensor and the center of the off-axis guider. Keep those the same. That way, if you're only changing out things in forward of the off-axis guider, it doesn't affect this spacing here, here, and you don't have to change the positioning of the off-axis guider camera and refocus. So this is important, and I've done that here. Plus, with these additional pieces here, I can get the back focus of about 85 millimeters. I have a video sometime back where I did a little study on this and decided, well, 85 millimeters seems to work a lot better in terms of star shapes in the corners than the 105 millimeter back focus that Celestron seems to suggest. That should give me a good and easy swap out configuration so I can go back and forth from the native focal length of the SCT to the focal length with the focal reducer and not have to mess around with the off-axis guider. Hopefully, that's the last time I had to play with this. Now, that off-axis guider and finding guide stars, what a pain this is. This is the orientation I had for the imaging camera, and then you can see I've got the off-axis guider rotated off by about 10 degrees over here to pick up this guide star. And the thing you want to be careful of when you're doing this is that this is only good for one side of the meridian. This yellow lines here, rotate those about 180 degrees. So now this guide camera switches around and is over here on the other side of the meridian. And so the reason I have it tilted a little bit is to make sure I had some space between the star here and the edge of the sensor, and also make sure I had distance between this star and the edge of the sensor. But you can see here, I just have basically two stars over on one side of the meridian and one star on the other side of the meridian. And this is the only place I can put this off-axis guider in order to have a star on both sides of the meridian. I could put the off-axis guider over here, but if you rotate that 180 degrees, you got nothing over here. So this is one of the difficulties with using an off-axis guider. Here's how the thing's set up as I look at the optical train from behind. That horizontal writing here on the ASI 294 is parallel with the long edge of the imaging sensor here. So you can see that's horizontal and that's horizontal. And then you can see my guide camera here and the off-axis guider is tilted off at 10 degrees. And I pull that number out of, again, the Stellarium Oculars view of this image here. And I make sure I have 10 degrees by putting a digital angle gauge up on top. I've got a video sometime back on that. Maybe I'll put that in the show discussion notes here, and you can watch it if you haven't seen that before. And it's pretty accurate. And one thing you can see why it's accurate is if I've been doing some imaging with this, and this is what the image looks like through PhD2. So I just took a screen capture of the PhD2 guiding window. You can see there's that bright star. There's the second star. You may not be able to see this, but it's there. And if I just go back and forth, you can see it's the same image. That's why it's important to be fairly accurate setting this up and to use Stellarium to find your guide star so that you know when you go outside and you've gone through a reliable procedure to set your optical train up before you go outside, you will have the guide star visible there when you finally start doing the images, and it won't catch you by surprise when, oh, I can't find a guide star. So now let's go over and take a look at how I refocus on the off-axis guide camera. So we're in Stellarium here, focused on Dubé there. I'm going to move it into the field of view of the guide camera so that I can have a bright star so that I can put the Bahtinov mask on and still have something to look at. Got to make the settings be the ones that we just showed you in the room there. And now I'm going to move it up to the center of view of the guide camera. And then I'm going to go over here and press Shift and left click on the mouse, and that puts in a marker at the center of the imaging camera. And now I can just framing assistant and bring the coordinates, and it'll eventually find it. Of course, I could use Stellarium to move the scope over there, but it wouldn't do a plate solve. And I need to have it fairly accurate to make sure that I'm at least in the proper position for finding the guide star in that small field of view that I have through the ASI 174 mini I'm using in my off-axis guider. Now it'll go ahead and expose and recenter the scope. Meanwhile, I'm going to bring up Sharp Cap. I use Sharp Cap to access the guide camera, and then I can use the Bahtinov mask with the sharp cap view to the guide camera, and then that's what will ultimately provide us with the focusing view with the Bahtinov mask. So we just need to find the ASI 174, bring it up, and I'll play around with some of the settings here to make sure that the whole sensor is in the view. Doesn't seem like we have Dubé in the field of view here, so that means move Dubé into the other side, 180 degrees away. So I'm going to rotate this 180 degrees. So that's the field of view of the guide camera when on the other side. And now I know it's this side of the meridian. And we'll just do another marker, Shift, left click, select, and go back over to, and we'll bring those coordinates in for marker 2. You can see it says marker 2 is the target name, and it finds, and it's just going to move the field of view of the imaging camera here to the other side of Dubé. And now we just need to do a slew. I don't need to do a slew and center here because it'll be in the field of view at this stage. And we can go back over to sharp cap, and there it is. And I'll just move it over to the center of the field of view of the ASI 174. It's the window for the GSS green swap server that I'm using to control the mount. And we'll just make a few adjustments here once we find out what arrow does what. And that's looking pretty good. And then move it up vertically a little bit. Doesn't have to be precisely in the center. We just want to have enough room so that we can see all of the diffraction spikes. And now I got to go out and put the Bahtinov mask over scope so that we can get those spikes. And I need to do an adjustment on the screen to bring out the brightness of those Bahtinov fraction spikes. And that's looking pretty good right there. Now I need to undo the set screw on the helical focuser and adjust it while trying to make a slight adjustment. Actually, it's in pretty darn good focus here. For a guide star, that's really all you need. But I'm out here, so I might as well do some changes. I will loosen the set screw on the helical focuser and then make some ever so slight adjustments just to bring that spike more into the center between the other two. Okay, making a slight adjustment here, and we'll see where we end up. I have to let it settle down because you are touching the scope. It'll finally settle down to a final image with the adjustment. There it is. Not much of a change. It probably can do with a little bit more of a change. So that's looking a little bit better. And let's see, right, make a little bit more of a change and then tighten down that screw on the helical focuser and call it a day. That's pretty good. Didn't have to make much of a change. As I said, I used that micrometer to make that 10 millimeter shift in the height of the camera. So everything was, I knew everything was going to be pretty good. And this just makes it a tad bit better. The thought that always occurs when doing all of these gymnastics with a off-axis guider is, do I really have to use that off-axis guider? It's really a pain. Right now, my imaging setup has a 0.41 arc second per pixel scale. With the off-axis guider looking through the same scope, of course, it has a 0.52 arc second per pixel. The pixels on the ASI 174, I think, are 5.86 micrometers, whereas the pixels in the ASI 294 MC are 4.63. So that's the difference. That's why it's a little bit higher for the off-axis guider and the pixel scale, but the numbers are very close, which is the big advantage of an off-axis guider, is that it lets you get down and form guiding at the same or nearly the same pixel scale as you have for your imaging camera. One thing that I wanted to do was to bring in the 200 millimeter focal length scope that I use with my GT81 and Red Cat 51. It has a Vixen base here. This is the William Optics Unigot 50. So I just thought I'll put a little L bracket on the top of the SCT. I have a little Vixen shoe that I got from ZWO some time back. I just attached it here. It's very solidly attached. The scope is very lightweight. Just slide it in, to a couple of thumb screws, lock it into place. I've got the cable. It's plugged in over here at the Ultimate Power Box, as is my off-axis guider. So they both guide scopes and the off-axis guider have been calibrated in PhD2. It's just a matter of switching from one to the other. The big question that I have is, now that I'm using a guide scope with 3 arc seconds per pixel, which is about 7 times higher, lower resolution or difference between the guide scope and the imaging versus the off-axis guider and the imaging scope, is that actually going to show up? One of the difficulties you have in performing a test like this is, if you did the off-axis guider on one night and the guide scope on another night, you'd have to wonder, how much did seeing change from one night to the other? Did that really affect the results here? Because seeing is a big variable here. Next thing that is a potential issue is imaging at one part of the sky with the off-axis guider, say, and a different part of the sky with the guide scope. So you want to be in the same part of the sky and the same seeing. And basically, the only way to do that is hot swap them in the middle of an imaging session. So that's what I did. I started imaging with the guiding with the 200 millimeter guide scope, and then I switched over to the off-axis guider after about 40 or 45 minutes. Here's what I saw as I'm looking at the half-flux radius history. You can see what I'm doing here. This is plotting the half-flux radius, which is related to the full width at half maximum and so on. And you can see the first 5 pictures I took were with the guide scope. Things started getting better as I was using the guide scope. It went from an altitude, the target, went from an altitude of 51 degrees down to 55, and then I switched over to the off-axis guider, and you can see the big step, big improvement in the guiding and in therefore the image quality of the images I'm taking when I switch to the off-axis guider. You can see that I'm in the same part of the sky, just 2 degrees different. This only took about 10 minutes to accomplish, and 6 minutes and 40 seconds of that are the imaging time. So this just took 3 minutes to make the switch between the guide scope and the off-axis guider. And that's a pretty telling result that we're seeing here in terms of difference. There's clearly a difference in a positive difference in using the off-axis guider versus the guide scope. Guide scope gives you more stars. You can use multi-star guiding, which helps to reduce some of the effects of seeing. I thought that would be a benefit. And it's, of course, easier to find guide stars. You don't have to worry about it at all. But with the off-axis guider, I may only have 1 star, so no multi-star guiding with the OAG at this focal length, just 1 star. So I lose that benefit, but yet still I'm getting a pretty obvious improvement, at least through the eyes of this real-time, on-the-fly HFR results from Nina. Now let's go over to these images, the first 5 with the guide scope, the next 5 with the off-axis guider, and see if this trend holds up by looking at the insight and what it can do for image analysis. This is what I got using the subframe selector. Now we're into the full width at half maximum. You can see that the trend is identical to what we were just looking at from Nina. You started off a bit high on the full width at half maximum. It came down a bit, and then I swapped out from the guide scope to the off-axis guider, and I got a zero point 0.8 arc second improvement in the resolution just by switching out to the off-axis guider. And then it was fairly consistent going forward after that. So clearly, the difference that we saw in the half-lux radius results from Nina are telling the same story that Pix Insight's subframe selector are showing. But we also have the ability here to go in and take a look at the eccentricity of the stars. And the eccentricity is a big story here too. With the guide scope, I was getting fairly eccentric stars. And here with the off-axis guider, I'm getting better stars, not what I want. I would I would live with zero point 0.4. I would prefer to see something around zero point 0.4. With an eccentricity of zero point 0.4, that just means that the star is longer by 10% in one direction than the other direction. When you start getting up into the zero point 0.6, you start to actually see this more. I think it's like 20% more, 25% longer in one direction than the other direction. And then, of course, the eccentricity here is way out, as you can see in this comparison of the two stars of these 2 images here. You're getting quite elongated stars going in this direction. This is primarily aligned with the RA axis, but there are some other effects we'll talk about. And you can see these stars. They clearly have some eccentricity to them, but they look a heck of a lot better than these guys do. That's for sure. So the guiding with the off-axis guider corrected for a lot of that eccentricity that I was having, but there are other effects going on. And some of that may be the fan vibration. I had fan vibration issues with my 294, replaced the fan in it, put another one in, and just by luck, it did improve things considerably, but it's probably still not done. I'm going to do another video after this one and talk about the fan vibration and how much it's contributing to this eccentricity problem, because there's only so much you can do with the optics before you just have to settle down and realize that it's the fan vibration that's creating the eccentricity, or at least contributing to it. And I want to know how much of that is actually the case. These facts are stubborn things, and they tell a pretty clear story here, which is the off-axis guider is the way to go with a long focal length SCT. It saves weight, saves image quality, preserves image quality at the cost of some upfront trouble in dealing with focusing and finding guide stars. Okay, well, another full moon, another opportunity to win some or learn some outside with the SCT. Had a lot of issues when I was out doing the plate solving with these tri-band filter I was using at the time, and it just failed all the time. Now, one way to solve that, of course, is to increase the exposure time, but you don't want to keep increasing exposure time, especially when you move down to a dual band filter, because that's just going to chew up focus time and plate solving time. So that was one of the things I wanted to check on, and also see if I really had to use that off-axis guider. Well, I swapped out my filter drawer, got a filter wheel, brought in the ZWO UV IR filter, and I'm using that for plate solving. And because the focus offsets are basically the same, I'm also using it for focusing as well. And so far, the results I've had with it are no different from when I was doing the focusing with and through the tri-band filter alone. And using Stellarium's marker and ocular features allow you to position the field of view of your guide camera on a bright star that you can use with a Bahtinov mask. Off-axis guiders are great, but they are a pain. We've seen firsthand here in this study that the off-axis guider does in fact improve your image quality by quite a bit. As I said, it's a win some, learn some, and in this case, I won, and that the filter wheel plus the UVR filter is solving all of those plate solving and focusing issues and cutting down on the amount of time needed to accomplish that. On the learn some front, we'll have to use and continue to use the off-axis guider. Okay, guys, well, that's all I have for today. Clear skies. I'll check in with you later. I want to come back and talk about those eccentric stars and fan vibration. Hang tight, and I'll be back with you in a little bit. Take care.